All right, let me give you the divergence theorem. All right, so first we need to recall what a divergence is. So if you want to take the divergence of a vector field F, remember how to do that?
Did we remember that?
It was mentioned
Yeah, I mentioned it really briefly.
after the review.
So do you remember this thing?
Yeah.
Yeah.
Which is like the kind of idea of
Gradient.
what you do for a gradient, right? It's not actually the gradient, it's just an idea. So this thing is the vector made of what?
Partial with respect to x, partial with respect to.
Perfect. So it's the partial with respect to x, y, and z. And then if I'm going to do this to a vector field F, right, there's two things I could do. Since F is a vector, I could either cross it, which is a curl, or I could dot it and get a divergence. So I'm going to take a dot product with the vector field F to get this thing. Cool. All right, so there's a good reason for it. We'll go over the geometry next time. But for right now, I just want to give you this object to play with. So the divergence theorem says if S is a surface, let me throw in piecewise smooth here. Meaning it can have sharp corners, but not lots of them, not infinitely often. So S is a piecewise smooth surface bounding a region W and F is a continuously differentiable vector field let me kind of point at continuously differentiable and add on a bigger region. What I mean by that is if this thing's got problems, they've got to be a bit away from the area you're talking about. Okay? In most cases, this won't matter at all, right? Most of our vector fields that we deal with are nice and continuously differentiable everywhere, but usually don't check this kind of thing. But I do want you to know that if this thing had problems where you were integrating, that would be a big deal. Cool? All right, so I've got a continuously differentiable vector field, a region W, and a surface bounding it. So that, to me, in my head, looks like this. I have some kind of a jelly bean, right? S is the whole surface. W is the whole inside. Just pull this. It's got to be the whole exterior, too. You can't run this on part of the exterior. You guys see that? So basketball on a shell or something kind of mushable to a basketball on a shell. Pull that. I need another caveat here. Remember that it matters which way we orient the surface, right? Okay, see that? There's two possible orientations for this kind of boundary S. There's sticking out and sticking in, right? So I'm going to add as outwardly oriented. If it's inwardly oriented, what do you need here?
Negative sign.
A negative sign. Cool. All right. So if we have all this, then the integral over the surface S of the vector field, the area. So what do you think with this thing? This is a this is a flux through the surface, right? And we're going to say, okay, and that's the total integral of the divergence of f. Ooh, okay. Hang on. What kind of thing is divergence of f?
No, it's number.
Yeah, so I took a vector field, right? That was a function of x, y's, and z's as a 3 vector. Then I dot product it with a
Another 3 vector.
so that's going to make some kind of scalar. You guys see that? This thing's going to be a scalar function. So it's got 3 variables in it. So how many things am I going to have to integrate to get a number? In other words, what should I throw here? Yeah, it's got to be the volume, right? So we're going to integrate over that surface W, or over the inside d volume. You guys see that? So this changes a chapter 19 kind of object, right? One of these flux integrals, into one of the old school, like, hey, you just integrate over the surface, no big deal. Cool? Alright, that's the idea.